And thanks to the organizers for putting on such a nice event. I've learned a lot over the past week and a half, and I'm excited to share with you what I've been working on. So one of the main themes in reverse mathematics that especially interests me are the tight connections between mathematical principles and computability theoretic notions. So most famously, this is shown by the omega models of RCA 0 having second order parts precisely the Turing ideals. So the Turing ideals are the ideals under the Turing computability relations. They're downward closed and closed under the effective join. And then we have similar characterizations for the other members of the big five. Second order parts of omega models of weak Koenig's lemma are the Scott ideals. These are Turing ideals closed under the existence of PA degrees. For any x in the ideal, you have a y that's just PA degree over x, also in the ideal. Second order parts of omega models of ACA 0 are the jump ideals. So they're Turing ideals closed under the jump operation. And that's about as far as I truly know anything about. I don't know very much about the higher computability side, but I included the next two on this slide just for the purpose of advancing a viewpoint. The second order models of ATR 0 are the Turing ideals closed under transfinite iterations of the jump. And there does have to be some nuance with how you formalize this, but I couldn't fit all that in the box, and I'm happy with what's written here. And the second order parts of pi11 comprehension are the hyperjump ideals. So these are the Turing ideals closed under the hyperjump. So these are the five very well-known systems of arithmetic, but we actually have a lot more equivalences between mathematical principles and computability theoretic properties. So here's a map of ones that we know about below ACA 0. And we can take some time just to stare at this diagram and meditate on it together. Here, how I like to think about this is all of these things are different forms, or it can be thought of as different forms of non-computability. So let's see. At the very bottom, we have this principle, and you don't really need to worry about what these actually say. You can Google them. But here, AST, this is the atomic model theorem with subenumerable types. And it's equivalent to, for all x, there exists a y such that y is not computable in x. This is an extremely weak principle, which is why it's at the very bottom. And this is really, in a sense, the weakest natural principle. This is really the weakest principle you could come up with that's not computably true, that relativizes. You could maybe come up with some artificial principle that's weaker than this, but it would not relativize. So this is maybe the weakest natural principle that's not computably true. And it just literally says there is a non-computable set. And at the very top, we have ACA, which says for all x, there exists a y, such that y computes x jump. And this is maybe the most classic or canonical form of non-computability, because the traditional way to show something is non-computable is show that it computes the jump. So up here we have like the most classic kind of non-computability. So depending on how liberal your imagination is, you could imagine all of these things as being some form of non-computability. Like over here we have diagonal non-computability, which is a special type of non-computability. What else? Hyperimmunity has several characterizations, but they can be thought of as different kinds. Like there's the block approximation version, or you could say it's not something not dominated by a computable function. So this could be thought of in different forms of non-computability. Other ways to look at this chart. Up here on the left, we have different versions of weak Koenig's lemma. So these can be sort of thought of as the compactness principles, because weak Koenig's lemma is said to capture compactness arguments, and then we can weaken the statement of weak Koenig's lemma in different ways to get weaker forms of compactness. We also have some versions of those principles where we've replaced x and y with x jump and y jump. So this is probably the least well-known principle on the board. The sequential thin set theorem for singletons with finite errors. And it's not very well known, but it is sort of a natural weakening of the cohesive set principle, because co is equivalent to sequential pigeonhole principle with finite errors. So this is just sort of like a weaker version of co. But so this can be thought of as like the jump compactness part of the diagram. And then this is kind of like a skew form of jump compactness where we have just y, but then also x jump. And then we also have generics over here, which is another important form of non-computability, if you will. Oh, and by the way, I should have said this at the beginning, but if you didn't notice the key. So all of these are strict implications, the double arrows. All the reds indicate non-implications. And this diagram explains everything that's happening both over RCA0 and over omega models. So the two different versions of implication agree with respect to all these principles. Okay, any questions about what I've shown here? So you have all of these, I mean, with Co, you have all these instances of the pigeonhole principle, and you need one set that solves all of them, but perhaps with finite error. So, yeah. Exactly, yeah. Cool. So there are still a few things that are not answered by this diagram. So these are the 4 questions that, as far as I know, are open. Yesterday, I heard a rumor that Rainbow-Ramsey's theorem for pairs, and I don't know how you say it, to like pre-image of size 2. I heard a rumor that this does not imply Co, but I have not seen a proof or reference for that, so I'm not, if anyone knows, I'd be happy to hear if this question is answered. The other 3 unknown questions are all asking about whether or not things imply the finite intersection principle. And I believe it is not a coincidence that we have open questions about whether things imply FIP, because a lot of times when you prove a separation, you do it through forcing. You construct some notion of forcing whose sets are nice in some way, where the problem you're trying to separate from does not admit solutions with that kind of niceness. But FIP says the existence of Co-1 generics, and Co-1 generics are very easily produced by forcing and have lots of nice properties. So you can't really prove any of these separations with a totally generic forcing argument, and you'd have to use some sort of effective analysis. Well, I could also add, like, for example, the only times we have separated one of these principles from FIP is you can separate OPT from FIP, but that's sort of an ad hoc effective construction that uses some facts about degrees. And then also we've separated things from OPT. Like you can separate weak Koenig's lemma from OPT using the hyperimmune free basis theorem. But that kind of argument would be no help for these 3 principles because these principles all do imply OPT. So you couldn't use an argument similar to the hyperimmune free basis theorem. Okay, I think that's everything I want to say about the diagram, unless anyone has any reflections about it they'd like to share. Okay.
Right? I mean, I will see you later. Ah, okay, yeah, yeah, I see.
Okay, great. So,
Can you
yeah.
remind
No.
me?
Okay. Okay, so what I wanted to do was so all of these principles that I've put in green, these are the principles involving non-computability or these 3 forms of compactness, as the title suggests. With some of these, we've added the jumps on both sides, and I wanted to situate these principles into a broader framework to really understand what's happening when you put jumps in front of x and y. So the main point of this talk is putting these green principles into a broader framework. And we do that with these definitions. So for each natural number m, we define the m jump versions of these 4 principles. So ASTM says for all x, there exists a y such that the m jump of y is not computable in the m jump of x. And similarly for the other principles. One way of understanding what these principles say is rephrasing the original principle in terms of delta 0m plus 1 descriptions. So like, for example, weak Koenig's lemma n can be thought of as saying, for all x, there exists a y such that, weak Koenig's lemma m could be thought of as saying, for any delta 0m plus 1 description of an infinite binary tree, you can find a delta 0m plus 1 description of an infinite path through that tree. And this interpretation maybe does sort of rely, or maybe this interpretation is more accurate over omega models. It might depend on exactly how you formalize these statements, but all of the interesting mathematics in this talk happens over omega models. So I think these are fair ways to interpret what these principles really say. Exactly, yeah, just that it's not computable, exactly. Okay, so everyone understand what these principles say? And we've seen some of them already. So weak Koenig's lemma 1 is the same as the cohesive set principle. DNR1 is this obscure sequential thin set theorem for singletons with finite errors. One interesting way of interpreting the AST, so as I said earlier, AST0 is the weakest natural principle that's not computably true. AST1, so it says for all x there exists a y such that y jump is non-computable in x jump. This could be thought of as the weakest natural principle that's not lowly true. That's not true in a model consisting only of low sets. And more generally, ASTM is the weakest natural principle that's not true in a omega model consisting just of low m sets. That make sense? All right.
Okay, sorry, can you say?
I mean, for example, in the cohesive set principle, the cohesive set principle is equivalent to, for all x, exists a y such that y jump is PA over x jump. And this principle does not imply ACA. So like, even in the case of code, this is a valid question.
No, I'm just asking how.
Okay, I mean, I guess you could formalize it directly by saying for any delta 0m plus 1 description of a tree, we have a delta 0m plus 1 description of a path. Yeah, I guess you could even just put the definition. Yeah. Okay, so these are the principles. And now here's the diagram. Here's how they all relate to each other. In this case, I didn't need any red arrows because no additional arrows can be added. So anywhere you see an absent arrow that can't be formed from the other arrows transitively, that indicates a separation. And just like the other diagram, this describes the situation over RCA 0 and over omega models. So this is kind of interesting. These ASTs form an infinite chain, an infinite ascending chain. But then for all the other principles, they're all incomparable to each other. So I thought this was kind of cool because here we have infinitely many principles that are all incomparable to each other, an infinite anti-chain. And that's kind of like a strong refutation of the phenomenon where everything is linearly ordered. So this is a very wide diagram. But so this is the picture. To prove that this picture holds, we have to prove the following things, and everything else follows from logical implication. So everything follows from ACA 0, and then for any fixed m, you can follow this chain down. So ACA implies the m version of weak Koenig's lemma, and so on, weak Koenig's lemma, DNR, you can follow the chain down. And then we also have, so point 5 describes this chain on the left, where these ASTs are all implying each other. So that's what we have here. If m is smaller than n, then ASTN implies ASTM. Points 1 through 5 are all perfectly straightforward. These implications you get by just generalizing the usual arguments that these things imply each other. The fifth one is also trivial. It just says that if the n jump of a set is non-computable, then the m jump is also non-computable, where n is greater than m. So all the implications are straightforward, and the separations are really where the interesting proofs come in. Now, these separations do use a lot of the same ideas, and if you see a proof of one of them, you likely can put together the proof of the other one. In this talk, I'm going to show you the proofs of these two separations. I think these two pair nicely to each other. They're sort of, the proofs are kind of parallel or even antithetical. And if you see these proofs, you can probably put together the other proofs, assuming you know the proofs of the base case where m equals 0. So we're going to show these two proofs. We're going to prove them using this separation framework that was used implicitly a lot and then explicitly written down by Ludovic. It says, so if you have a weakness property, which is some collection of sets that's downward closed under Turing reduction, so some sense in which sets could be considered weak, we say that an instant solution problem, I think I meant to use a different font for that P, but we say an instant solution problem preserves this weakness property if for any weak set Z, and any instance of the problem you can compute in that weak set, you can find a solution to the instance that is weak. And it's even still weak if you combine it with this other weak set we have. So this notion of preservation is useful because you can use it to get separations over omega model. So if you have two instant solution problems, and one of them, P, preserves the weakness property, and the other one does not, then P does not imply Q over omega models. And you can prove this by iteratively constructing a Turing ideal, all of whose sets are weak in this sense, satisfying the first problem but not the second. So, in order to prove separations using this framework, the first step is coming up with the right weakness property. And in problems that are stated in such explicitly computability theoretic terms, it's very easy to choose the right weakness property. You just choose the one given by the problem that you're trying to separate another problem from. So in this case, we would choose these weakness properties. So in this, on this slide, we're showing as like a warm-up the base case where we have m equals 0 and n equals 1. So I just want to show you these separations in the 0 and 1 case. So to prove that weak Kernig's lemma 0, which is just plain weak Kernig's lemma, to show that this does not imply AST1, so this is the weakest principle that's not lowly true, we'll take our weakness property to be the set of all low sets, because clearly AST1 does not preserve this weakness property. And then similarly here, we're trying to show that the cohesive set principle, remember that's weak Kernig's lemma 1, to show that the cohesive set principle does not imply DNR, our weakness property will be the set of all non-DNC sets, because clearly the principle DNR does not preserve that weakness property. So these choices of weakness property make sense? So now, to prove the separations, well, in this case, we have to show that we can solve weak Kernig's lemma by only taking sets that are weak in this sense. So we can solve weak Kernig's lemma using weak sets. And that can be done using the famous low basis theorem, because the low basis theorem says precisely what we need, that we have a set G that is of PA degree, so it does solve weak Kernig's lemma, but it's low. Now, really, to use the framework explicitly, we need a relativized version of this, because remember, the separation framework requires our set to be weak even when we combine it with some other set that's also weak. So the relativized version that we need is that for any Z that is low, we can find a G such that G is of PA degree, but G is still low even when you combine it with Z. And the usual proof of the low basis theorem can be, it also proves this. So now to prove this other, so this low basis theorem combined with the framework proves this separation. Now to prove this separation, one way we can do it is using this other theorem that I found in Ludovic's book, I don't know if it appears anywhere else, this is the first place I've ever seen it, that is sort of antithetical to the low basis theorem. So this theorem says, I've already stated it in the relativized form, for any z that's not DNC, and for any arbitrary set A, we can find a set G such that G is not DNC, even when we combine it with Z, but the jump of G computes this set A. So the reason that this theorem is antithetical to the low basis theorem is that the low basis theorem says we have this set G that is strong. G is of PA degree. However, the jump of G is as weak as possible. So this one says we've got a G that's strong, but its jump is weak. Here we have the opposite. Here we have a set whose jump is as strong as we want it to be. We can take this G to compute any arbitrary A. However, this set G itself is weak. G is not DNC, even when we combine it with some other set that's not DNC. The low basis theorem says we have a set that's strong, but its jump is weak. This theorem says we have a set that's weak, but whose jump is strong. So the reason that this theorem gets you the separation we need is that we can choose any A we want. And in particular, we can choose an A that, for example, is of PA degree over 0 jump. And then we get what we need. So everyone see how these theorems get us the separations? Another question. So the only place I've seen this, it appears as an exercise in the book that Ludovic has on his website. And if it appears anywhere else, I'd be curious to know that, but I've never seen it anywhere else. Okay, so here are the two separations that I told you I was going to prove. The same separations, but the general iterated jump form with M and N. Again, we just choose the obvious weakness properties. So these are precisely the weakness properties that are directly not preserved by these problems, following directly from the definition. So we have to show that we can solve weak Kernig's lemma N only using sets from W. And over here, we have to show that we can solve weak Kernig's lemma N only using sets from W. And the theorems we're going to use to do it are just the iterated jump versions of the two theorems from the previous slide. Here they are. So here we have the iterated jump version of the low basis theorem. So here, for any z that is n low, so the n jump of z is computable in the n jump of 0, we can find a g such that the m jump of g is strong. So the m jump of g is of PA degree over 0m. However, the n jump of g is weak. So g is low n even when we combine it with z. And then again, over here, we have the iterated jump version of that other theorem. So this says for any z whose m jump is not DNC over 0m, and any arbitrary set A, we can find a set G whose m jump is weak. So the m jump of G is not DNC over the m jump of 0, even when we combine it with this set Z. But, well, actually, in this case, we have something even stronger. Because what you might expect based on the pattern is me to have an n here. The n jump of G is strong. But we can actually do something even better than we need. We can even just have the m plus 1 jump of G be strong. So then in particular, the n jump of G will also be strong. So this theorem is actually better than what we really need. So if we can prove these two theorems, then we've proven the separations. The top theorem is actually pretty easy to prove. You can do it by directly combining the low basis theorem with Friedberg's jump inversion theorem. So this top one can be a nice, it's very straightforward, just applying those theorems. This one actually involves a little more of a complicated argument. And the reason this one is more complicated has to do with the order of m and n. Because m is less than n, it's easy to just do the low basis theorem relativized and then just jump it down. But in this case, you would have to sort of jump it up, and that doesn't really work. So we're going to prove this one directly. And that's what the rest of this talk is devoted to, is proving this theorem. So before we dive into that, any questions? Okay, So let's go ahead and prove it. Here, I've just restated the theorem. And actually, we're going to prove it by induction on M. And in order to make that induction go through, we actually need a relativized version of it. So here I've stated the relativized version we're going to prove in order to make the induction work. So here, we're relativizing all of this to some degree d. So for any degree d, and any set z, such that Zm is not dnc over the m jump of d, and any arbitrary set a, we can find a set G such that the m jump of G is not dnc over the m jump of D, even when we combine G with this other set Z. But the m plus 1 jump of G is as strong as we wanted it to be. This is what we're going to prove. I'm actually going to write it down just so we can have it up here as we go through these slides. Let's see. For any D, for any Z, such that the m jump of Z is not dnc over the m jump of D, and for any A, there exists a G such that the m jump of G, when we combine it with Z, is still not dnc over the m jump of D, but the m plus 1 jump of G computes A. So I've just written it here, so we have it. And I know I said I wasn't going to erase anything else, but maybe I'll also draw a picture just to show us what's really happening. I have lots of time. I'll do it the fun way. Unless you want to do it, Georgia. Is this the right thing? Like, what do you mean one? Oh, like this? Oh, okay. I see. Yeah, I heard that was the hard part. You're supposed to do that for me. Okay. So just a picture of what this theorem says. It says that for any set D, and then any set Z, I'm gonna get rid of the dot, move it lower. So for any set D, and any Z, such that when we look at the m jumps of these sets, we have that Z, so this is all part of the assumptions. So Zm is not dnc over dm. So this is part of our assumption. And then also, just for any arbitrary set A, so normally we're going to take A to be something pretty strong. So like for any set A, we can find some set G, it's generic, so it could live anywhere, such that, okay, I'll put it down here. So we have this set G such that even when we combine G with Z, and then look at the m jump of that so here we have the effective join of G and Z, then we look at the m jump of that. So that is still not dnc over the m jump of D. Here's GM. However, so the m jump of G is weak because it's not dnc over dm, even when we combine it with Z. However, the m plus 1 jump of G is as strong as we wanted it to be. It computes this arbitrary set A. Everyone follow this picture? Okay, so this is what we're going to prove the rest of the time. Yeah, so the assumptions are we have this D, we have this Z, with the property that the m jump of Z is not dnc over the m jump of D. So those are the assumptions, and then the theorem tells us there exists this set G, such that when we combine G with Z and look at the m jump of it, that's still not dnc over D. However, when we look at the m plus 1 jump of G, that computes this arbitrary set A. Oh, no, that's a misleading part of the picture. Thank you. Thank you, yes. I drew it wrong. There we go. That's better. Thank you for that. Yeah. All right, so I'll move over here just so you can see the picture better. We're going to prove this by induction on M. For the base case, M equals 0, just reading that out. So for any D and any Z such that Z is not dnc over D, and any A, we can find a G such that Z plus G is not dnc over D. And the and just the jump of G computes A. So we're going to prove this using Tausner forcing, which Ludovic mentioned during his lectures last week. Tausner forcing is a great notion of forcing for producing sets that are weak, but whose jumps are strong, which is precisely what we want here. So we're going to use a forcing whose conditions are pairs GK, where G is some finite partial function taking in pairs of numbers and giving us a 0 or a 1, and K is just some natural number. Now we define extension, so we say a condition HL extends a condition GK if H extends G as a function, if L is a bigger number than K, and for all new pairs that we added to the domain. Because remember, these functions take in pairs. For any new pair that's in the domain of H that wasn't already in the domain of our previous condition, if the first input is smaller than the natural number from our first condition, then we have to copy this set A. And the point of this condition, which I explicitly state on the next slide, is to guarantee that when we take a generic set, so a generic filter induces some function just by stitching together all the finite functions we have. And the point of this last condition is to guarantee that taking the jump of our generic set will compute the arbitrary set A. And that's using the limit lemma, Schoenfeld's limit lemma, because so these are functions on pairs. So it looks like a big grid of numbers, a big grid of zeros and ones. And then if we look at any particular column, eventually that column is just going to copy down A. And it starts copying down A, that column, say the ith column, will start copying down A as soon as we include a condition whose natural number part is bigger than I. Because once we have a condition whose natural number part is bigger than I, well, we're going to stay that way because we only increase the natural number. And then we're forced to just copy down A at that point. So by the limit lemma, any generic function will have a jump that computes A. Okay, so I state this explicitly. So let F be some generic filter. By the limit lemma, the jump of this function computes A. So the only thing remaining to prove is that this function is not dnc over D. So what does that really mean? What that means is that for each condition and for each index, we have to find an extension of this condition, forcing the ETH function relative to our generic set combined with Z not to be DNC. And there are two ways that could happen. One way it could happen is converging to the wrong value. So we could find a condition forcing the ETH Turing functional relative to Z joined with our generic to converge to this wrong value. Because if you converge to this value, you're not going to be DNC. Or you can force it to diverge. So this is just writing down what it means to force the ETH function not to be DNC. So the proof, for those who were at the summer school, is going to be in that form of these trichotomy proofs that Ludovic kept showing us. So define this set U to be a set of, so X we're going to think of as an input. So the set of pairs, X we're going to think of as an input to a Turing functional, and V we're going to think of as a value that it could take on. So the set of all pairs of inputs and values such that there exists some condition forcing the relevant Turing functional to converge on this input to this value. So this is like the set of all possible input-output pairs that we could force from our condition. So we're not guaranteed to force a given input-output pair from this set, but this is the set of all input-output pairs where there exists some extension forcing it to converge to this value. So this observation will come in handy later, but if you look at the definition, this set is sigma 0, 1 in Z. This is maybe not entirely obvious. I mean, we have an exists, so we're quantifying over conditions. The Z in here comes from this Z. But you might ask a question about this claim, because remember, the definition of extension also involved that arbitrary set A. Going back, here I've defined what it means to extend, and we did include this set A. So you might ask, okay, shouldn't we really have sigma 0, 1 and Z plus A? But really, we're only looking at extensions of this particular condition. And to look at which conditions extend the condition GK, we only need to know the first K bits of A, and that's finitely much information. So that's why we don't need Z in this definition. So in other words, the forcing condition, or the extension relation, is not uniformly computable, but it is for any given condition, you can compute that. Okay, so as promised, we have three cases. So the first case, suppose that there is some X such that the wrong value, so the value that makes the function not DNC, does appear in this set of possible input-output pairs. So there's some X such that the pair X together with phi sub X of X relative to D is in the set. So, I mean, well, what does this set say? This set is giving us the set of all input-output pairs that we could force, such that there exists some condition forcing this functional to take on that value. So in this case, we have exactly what we need. We can just take the extension, witnessing this input-output pair to be in the set, and then by definition, this condition forces the relevant Turing functional to converge to the wrong value and not be DNC. Case 2, suppose there's some X such that for every possible value, X and that value does not appear in the set. So remember, the set is telling us all of the possible input-output pairs. And here we're saying there's some input that is not linked to any output. So there's no way that we could force this Turing functional to converge on X to any output. This case is even better, because the condition that we have already, GK, forces this to diverge, because there's no way that we could force it to converge to any value. Third case, suppose neither of the above happens. So in this case, we don't have any input-output pair with the wrong value, But for every x, we do have something that it's connected with. In this case, we can use the set U to compute the graph of a DNC function. In some of the trichotomy arguments, the set U is already a graph. In this case, that's not exactly what happens because we still could have some x that appears with multiple different v's, because we're taking on natural number values. But from U, we can compute a new set, say U0, where we just match x with the least v that it's paired with in the set. So that'll give us the graph of a function. We know the function is defined everywhere because for every x, it was paired with some output. And we know that output is not going to be the wrong value. Therefore, this U0 is the graph of a DNC function. But now, because this set U is sigma 0, 1, and z, that contradicts the assumption that z is not DNC over D. Everyone follow that proof? Okay, so this is the base case for our induction. Now let's prove the inductive case. So we're going to assume, here, I wrote it up here. So assume this is true, precisely what's written. And what we're going to prove is this statement, but with all the m's replaced with m plus 1s. So in particular, that m plus 1 down there is going to be an m plus 2. Okay, so we're going to use the inductive hypothesis, but relativized. So in the inductive hypothesis, we're going to plug in z prime and d prime for z and d. So, well, it's probably best to just read the slide. So precisely by the inductive hypothesis, but plugging in z prime for d prime, there exists some set, I'm calling it G0 in this case, such that z prime combined with g, the m jump of that, is not DNC over the m plus 1 jump of d. So the reason we have m plus 1 jump is because over here, I wrote d and d instead of d and c. But over here, we have the m jump of d, but we were plugging in d prime for d. So that's where the m plus 1 jump of d comes from. And then the m plus 1 jump of g computes a. So this is what we get precisely from plugging in z prime and d prime for z and d. And the forcing is going to actually be very similar. Basically the exact same forcing, actually. Oh, okay, but actually there's a typo here. It's not exactly the same forcing. So there's one typo where I have a of x here. That's actually supposed to say G0. It's supposed to be the generic set from our previous step. So actually what this is supposed to say is h of x, y is the generic set that was produced in the inductive hypothesis. So sorry for that typo, but this is what it's supposed to say down there. So our forcing is defined in terms of the set we got in the previous case. Okay, so as before, a filter induces some function by stitching it all together. Let f be sufficiently generic. Okay, typo again. So by the limit lemma, f jump computes, it's supposed to say G0. I was copy pasting things. So it's supposed to say the jump of this generic object computes G0. And the reason this is good, the reason this is what we want, is because by hypothesis, the m plus 1 jump of G0 computes A. So what that means, so this implies that the m plus 2 jump of our generic object computes A as needed. Does that make sense? So that's why we wanted G0 in place of A, because then we can apply the inductive hypothesis to get what we need. Because we want our generic object to have an m plus 2 jump that computes A. So all that remains to prove is the non-DNC part of our goal. So we have to prove this first bullet point up here, but plugging in m plus 1. So we have to prove that the m plus 1 jump of G combined with Z is not DNC over the m plus 1 jump of D. The proof is very similar to the proof in the base case, except the set U is considerably more complicated. Okay, so this is just writing down what we need. So for each condition G and each index, we have to find some extension, forcing the generic object to have an n+1 jump that's not DNC. So forcing the n+1 jump, well, you can just read that. Okay. So we're going to define the set U in terms of what Ludovic calls a forcing question. So fix some condition and fix some formula that is sigma 0 I in Z. So here, this formula is sigma 0 I formula phi. Could be, there's supposed to be an x here. Exists an x such that psi of the generic object in x holds, where psi is some pi 0 I minus 1 formula. So there's supposed to be exist an x there. So here's how we define the forcing question. And this is going to be what appears inside the definition of that set U, generalizing the set we had in the base case. So this is a more powerful version of the set U. So in the base case, I equals 1, this definition is just what was in the definition of U from last time. So if I equals 1, I actually don't know how to pronounce this. I would say, let's say the forcing question will answer yes for this condition and this formula if there exists some x and some extension such that psi holds of this x and that extension. So even though h is finite, so here a condition has some finite function. In this case, psi is pi 0. So by the use principle, we only need finite much of the object to decide this formula. So this definition is just what we had in U. It says the forcing question holds if there exists some x and some extension such that this literally holds. Not forces this, just so that it holds. Now, the inductive part looks exactly the same. So for any I greater than 0 or I greater than 1, we say the forcing question holds if there's some x and some extension such that now the only difference is we're not asking this psi to hold, but we're asking that the forcing question of the, oh, okay, I think there's actually another typo. There's something wrong here. I think I got the negations. Yeah, that would make sense because psi, yes, because psi is a is pi. Yes, thank you for that. Okay, yeah. So what this is supposed to say, because we're only defining it explicitly for for sigma I formulas. So based on what I've defined here, this condition does not make any sense because psi is a pi formula. But so we're saying it does not hold. So what that should really say, correcting another typo, should really say that L, the forcing question, does not hold for the negation of the previous one. That makes sense? Okay. So here are the properties we need. So I'm going to claim some nice properties that this forcing question exhibits. So take some sigma 0 I formula. So first of all, we have, as before, some observation regarding the complexity. So in this case, the complexity of saying the forcing question holds does depend on G0 to some extent, because unlike the previous case, we're not just using finitely much of G0. When we iterate this, we do need to use some information about G0. So this looks kind of strange, but this, as you'll see, is precisely the complexity that we need it to have. You could imagine if we didn't have any dependence on G0, if you got rid of the G0, this would make perfect sense, because this would be sigma 1 in well, the I minus 1 jump of z, which is the same as sigma I in z. So it would make sense that this force in question is sigma I, because it's a sigma I formula. However, we also have this dependence on g mixed in there. So this looks very similar to the case analysis in the proof that you're about to see on the next slide, and the one we saw a couple slides ago. So if the force in question does hold, then we can find some extension forcing the actual formula. On the other hand, if the force in question does not hold, then it's even better. We don't need an extension. Then our original condition just forces the negation of this thing. So in Ludovic's terminology, putting these two conditions together implies that this is a force in question. And then this third condition says that the force in question is pi 0 I extremal. Because here we don't need to find an extension, it just automatically forces it. And then he doesn't really have a word for this thing. This is some special complexity property that gets us exactly what we need. Okay, we're almost done. Now we just have to do the proof, but it's exactly the same as the proof we've seen before. So we define U to be the set of possible input-output pairs. Well, so here, take phi to be some sigma 0 m plus 2 formula, asserting the relevant thing, so asserting that the relevant Turing functional on this input converges to that output, so analogously to the first case. This is the case of possible input-output pairs according to the force in question. By the analysis, or by the claim on the previous page, this is the complexity. And again, we have these cases. So if we have the correct value or the wrong value, then we can just, by the claim, there exists some extension forcing it to converge to this value, and then we force the relevant functional to converge to the wrong value. It's not DNC. On the other hand, let's say there's some x that does not come with any possible output. In this case, using, again, part of the claim, in the terminology, the fact that the force in question is pi 0 I extremal, this condition itself forces it to diverge. We're actually in more of the terminology, what we're really using is the fact that pi 0 I extremal implies omega merging, or like omega pi 0 I merge, countably pi 0 I merging, because we're merging all these different things, these countably things that don't happen. And then if neither of the above happens, here the complexity is precisely what we want, because this z prime, the m jump of z prime combined with g0, this shows up directly in our hypothesis, because remember we took z prime for z, so this contradicts directly our hypothesis that this thing is not DNC. And then you've proved it. Any questions on that proof? Okay, and that is everything I have, so thank you. And here's another picture.